All right, so we're pressing forward in this chapter on thermodynamic properties, and we're closing in ideal gases. We're probably not going to be able to finish everything today. If I can have your attention, please. Thank you. So last time we talked about the ideal gas model. That includes the equation and the observation experimentally determined. Who did the experiments? Joule. He had two chambers, vacuated one, had ideal gas in the other, and he deduced that the internal energy is a function of temperature only. And likewise, then because H is defined as U plus PV, and PV is equal to RT, hence H is a function of temperature only. So what is the definition of C sub V? Is it defined as the rate of change of U with respect to temperature holding V constant? Now, why do we have a partial derivative there? Because normally U is a function of maybe temperature and volume, temperature and pressure, two independent intensive properties, fix the state, and I can get other properties. So you think of most of these properties as being a function of two other properties. But when U is a function of T only, for an ideal gas, what do we know about this partial derivative? Can it be turned into an ordinary derivative? Can it be turned into an ordinary derivative if U is a function of temperature only? Yes, it can. And then one of the things we like to do with this is we like to separate and integrate. And what we find is that the change in internal energy for an ideal gas is just the integral of C sub V dt, and often C sub V average over that temperature interval times the size of the temperature interval, T2 minus T1. So U2 minus U1 is C sub V dt for an ideal gas. Now, a lot of students love this equation. They get excited about it. Then they forget that, hey, that's for an ideal gas. Then they go and apply it for all kinds of real gases in the two-phase, liquid vapor region, all that. Don't do it. Don't do it. Don't do it. This is a number of assumptions in this, right? Ideal gas. Can you do the same thing starting with H, thinking about H as a function of temperature and pressure? You define C sub P as the rate of change of enthalpy with respect to temperature holding pressure constant. If it's an ideal gas, then C sub P, hey, it's only a ordinary derivative of enthalpy with respect to temperature. And you get H2 minus H1 is equal to C sub P average times T2 minus T1. So, at most, the specific heat constant volume for an ideal gas is a function of temperature. Not a function of temperature and volume or temperature and pressure or temperature and another property. Just a function of temperature. And likewise, C sub P for an ideal gas is only a function of temperature. Let's take a look at some of the temperature dependence on that specific heat for ideal gases. This is a real important figure. I know all the figures are important in the textbook, but you know, this is probably up in the top 5 or top 10 when I teach Thermo 2. Students ask questions like, let's go back to chapter 3 and let's look at this figure for a minute. All right, so now what's on the x-axis? Temperature. What's on the y-axis? Well, it's kind of a funny. It's CP bar divided by R bar. Now, I understand R bar. The name of that one is the universal gas constant. I remember its value in SI units, 8.314 kilojoules per kilomole Kelvin. We use that a lot. Is that the same R bar that's in the equation? P Let me write it this way. PV is equal to N R bar T. It is. It's the same R bar. C sub P bar. What is that? That bar on top of the C sub P must mean average. I've seen that in other textbooks, other classes, but in this textbook, nope. What's the bar mean on top? It's specific per unit amount, so not per unit mass. So let's try and remember, I don't know. How about as a review, what was lowercase v? That was volume per unit mass. But if you see this term, lowercase v bar, what is that? Volume per unit amount. N is in kilomole, true? Meters cubed per kilomole. So that's helpful to remember. So we got C sub P, that was our specific heat, constant pressure. And we recall, just like the units on this one is meters cubed per kilogram. This one was meters cubed per kilomole. We think about our units for C sub P, kilojoules per kilogram Kelvin. And if I said, well, what are the units of C sub P bar, the one we're trying to understand right here, it would be what? Kilojoules per kilomole Kelvin. So instead of being per unit mass, it's per unit amount in kilomoles. Okay. So what is some of the, well, I recall that we had the amount, and then we could jump back and forth between amount and mass using a property, big M, but I forgot the name of big M. Molar mass. Molar mass. So first clicker question today is, do I take the number of moles multiplied by the molar mass, or number of moles and divide by the molar mass to get the mass? Answer A, if this is correct, or answer B, if that's correct. We'll take your answers. I want to know, how do I jump back and forth between N and M using cap M, the molar mass? All right, let's take a peek. So we're not unanimous, but we're pretty close. Right? Isn't that correct? What are the units on big M, the molar mass? Kilograms per kilomole. Kilograms per kilomole. So let's take a look at another one. I want to be able to go back and forth between C sub P bar and C sub P. So should I multiply by M, or should I take C sub P and divide by M? Which one of those is correct? Answer A or answer B? I'm given C sub P. I want to calculate C sub P bar. Do I multiply by big M or divide by big M? Okay, didn't give you a lot of time, right? Let's take a look. Let's chase units to help determine what is the right answer, okay? So C sub P, just looking at C sub P, kilojoules per kilogram Kelvin. If I go over here, I want kilojoules per kilomole Kelvin. I better put kilogram per kilomole there. True? Cancel the kilograms, leave me the kilomole per kilomole. So I multiply by Is this guessing? What's going on here? A little more evenly. Do you want to do another one? New page. Another one. I have R. And I have R bar. Should I multiply by M or divide by M to go between R bar and R? Well, units will help us determine, right? R bar would be kilojoules per kilomole Kelvin for R bar, true. And then if I want to kilogram per kilomole, then the kilomoles cancel and I have kilojoules per kilogram Kelvin, which is the units of R that we want. So the correct answer is true? True. So let's take a look here. We understand now more of what's on this axis. What's on that axis? Specific heat, constant pressure. Somebody says, I really want, let me do this. I have to erase some parts up here, okay? Well, maybe not. Maybe I'll try and tuck it in. So if somebody says, I want to go out at this temperature right here, 1,000 Kelvin. And I want to do it for carbon dioxide. I would read off a value of 6.5. I'm not going to be that accurate, okay? 6.5. So C sub P bar divided by R bar is 6.5. So C sub P bar is equal to 6.5 times R bar. I know what R bar is, right? And then somebody says, no, I want C sub P. I want it in units not per mount, but per mass. So then what do? We take and multiply by the, divide by C sub, is that a P? That's a P. C sub P divided by M, true? Then somebody else says, do they have a plot for C sub V, specific heat constant volume? Well, let me work that out for you. They don't have a plot, but it's embedded in here. So let me insert new page. So what is C sub P? What is it defined as? The rate of change of enthalpy with respect to temperature for an ideal gas. It's an ordinary derivative. So if we start from the definition, here, I can start from H is equal to U plus PV. True? Is that equation good? Is that equation good only for ideal gases or for everything? Everything. Two-phase liquid vapor mixture, that's just the definition. Now, I can rewrite this as RT. What? What did we just do there? Limited this to ideal gas only, because PV is equal to RT, right? All right. If I take that equation and I say I can differentiate every term in that equation with respect to temperature. So let's just go ahead and do it. We'll get derivative of H with respect to temperature, derivative of U with respect to temperature. We'll use the chain rule. So we have the derivative of R with respect to temperature times temperature plus R times the derivative of temperature with respect to temperature. Did I do the chain rule correctly? Yes. All right, here's another clicker question for you. I'm really interested in this term. That term, is it less than 0? Is it negative? Is it equal to 0? Is it greater than 0? Is it positive? Can you tell what that derivative of R with respect to temperature is? Answer A, B, or C. And there you go. What is dr dt? Everybody in? Oh, you got to go fast. I can't. All right, so a lot of people believe that it's equal to 0. Why is that correct? It's a constant. What's the name of it? Ideal gas constant. Constant. Let's see. If I change temperature, does the constant change? Nope. It's not a function of temperature. Hence, that's correct. B is correct. Now, let's do this one, but I won't do a clicker on that one. 1. This is the easiest derivative. Don't get too caught up. Can you do the inverse hyperbolic sinh, or some other crazy derivative function? This is so easy. It's equal to 1. So what do we get when we have? We have the h dt is equal to du dt plus r. Did I make an error, or is that equation good? What is this called? What is this called? For an ideal gas. This is all for an ideal gas. And so we see that if you give me C sub P, I'll give you C sub V. C sub V is simply C sub P minus R. That's it. So when we go back to that plot, that had a lot on that y-axis. Because I can give you, or you can give anybody, C sub V is equal to C sub P minus R. So even though they only put C sub P on there, you can get C sub V just as easy. All right, a little bit of work, you can get it. Now, did I leave you enough time on this slide? Did you get it all? Even if it didn't, it's in the book, right? That you own and that you read. True? Yeah, of course. Yes, sir. No, I wouldn't memorize it, but you should have a mental image like of the PVT surface. You should have a mental image of this. This is not tricky. This is easy. Numerically, let's continue on this plot, okay? Because I'm not done with it. Let's take a look. There's something in common about these two top curves, something in common about this group of curves, and something common about that single curve. Can you see the pattern? Sometimes it's better if a student observes the pattern by themselves, as if discovering the pattern by themselves instead of just everything being told. What's the pattern? Yeah, this is more complicated molecule. This molecule has 3 participants. This one has 3 participants. Each one of these have 2 participants. Air is primarily nitrogen and oxygen. Both of them are 2 participants. They're diatomic. If you want to call it triatomic, diatomic. And then what about down here? Argon. Noble gases. Monoatomic. They float around by themselves. They're not typically linked up with anything. So these have the more complicated molecule and the more temperature-dependent specific heat. It's more strongly temperature-dependent. What is the least temperature-dependent of the whole group? Those monoatomics. All right. So if I say, give me for helium at 1,000, you're going to come up and you're going to give me 2.5. Okay, 1,500, 2.5. 2,000, 2.5. That's the type of function we love in engineering. Easy, right? It's always 2.5, regardless of the temperature. For monoatomics, the specific heats are not. From this plot, you can tell. They're not a function of temperature. So when I give a problem in Thermo 2 and I say, helium is the working fluid. Student says, helium. I need the enthalpy of helium. I can't find the tables for helium, professor. How come you didn't give me the tables for helium? I can get air, I can get temperature-dependent specific heats or enthalpies or internal energies for CO and CO2, but I can't get it for helium. Then I got to go back, chapter 3, go back to this plot. True? All right, so let's. I think I've exhausted this one. Let's move to its cousin equation, or table I should say, A21, which has an equation which is a curve fit. It's a polynomial curve fit of C sub p bar divided by r bar. It's what was plotted in that plot that we just looked at. So we have a constant, then a constant times temperature, constant temperature squared, etc. This, whenever you have a curve fit like this to data, it's great for interpolation in between, in a range. It's terrible for extrapolation. The polynomials wiggle and they shoot up and down after. So don't use this one for temperatures less than 300 or temperatures greater than 1,000. You ever seen a plot of polynomials curve fit in a range and then extrapolate beyond that range? You should. And then you'll know, oh, don't trust it. So here's for the gases, here's your alpha value, your beta value. Oh, what's this 10 to the 3 mean? That means if I want to put a beta, do I take, for oxygen, do I take this value and divide by 10 to the 3 or multiply by 10 to the 3? I'm a little divided here. Yeah, you would put 0.0018, whatever that is, 78 with a negative sign. You divide by 10 to the 3 because what they're doing in this textbook is says they took beta, they multiplied by 1,000 and stuffed that into the table. So when you want the value out, you take the value out of the table, divide by 1,000. Notice right down here, what is that? Monoatomic gases. What is a little A? Go to footnote A. For monoatomic gases such as helium, neon, argon, C sub p bar is constant over a wide temperature range, not all the temperatures in the world, but over a very wide temperature range, and is very nearly approximately equal to 2.5 times R. That's the same. 5 halves is 2.5, isn't it? Yeah. And so this right here. So that's how you would get the change in enthalpy or change in internal energy for helium without any tables. Okay. If you do have air as your working fluid and it's behaving like an ideal gas, and that's very, very common, then you want to have as accurate as possible. You would want to have the changes, let's say H2 minus H1 is equal to the integral of C sub p dt. Well, what they did was they said, let's start this always at a reference temperature, T ref, and go up to our temperature of interest. So then we can just plot or get H as a function of T. That's nice. And so when you want, you get H1, let's say, is the enthalpy at 300 Kelvin for air. So they made a nice table. Here's the temperature. You'd come down to 300, and you'd get H right there. Embedded in there is a reference temperature, but you're always going to take a difference in enthalpy. Just like we had a datum point for our steam tables, refrigerant tables, this has embedded in it a reference temperature, starting point. Okay. We don't worry about it right now. What about U? Yes, U is a function of temperature. So this would be the most accurate data for internal energy and enthalpy for air. Notice the table's kind of split and they have the temperature, then it comes over here, temperature again. So you have 2 columns to the temperature. What about this S naught and all this right here? That's all associated with entropy. And that's chapter 6. We'll get to it later. Second law. But right now you can understand the first 3 columns, temperature, enthalpy, and internal energy for air. You also have temperature-dependent properties for carbon dioxide. You also have it for carbon monoxide, water vapor, and oxygen. There are some limited ideal gases that they do have temperature-dependent properties for. This table A23, is a little different though. Here's your temperature going down in Kelvin, but what did they put right here? H bar. Okay, instead of H, what does that bar mean? Yeah, it's per unit amount. So they tell you right up here. Can you read that? This H is a function of T and U is a function of T are in units of kilojoules per kilomole. So we're going to solve a problem in a second. And if I wanted H2 minus H1, I could get out of the table H2 bar minus H1 bar, knowing the temperature H at T2 and H at the temperature T1. And what would I do to get the difference in H if I had the difference in H bars? Multiply or divide by the molar mass? Should I either multiply by M or divide by M? A or B? I have delta H bar, and I want to get delta H. No, the change in H is equal to the change in H bar times or divided by big M. All right, we're done. We're not unanimous, are we? Who answered B? Why did you answer B? Because you're probably thinking what the units of big M are. And the units of big M are kilograms divided by kilomole. And I need H in kilojoules per kilogram. True? So your actually units really help us here, guide us to the right formula. So B was correct. True? All right. So I know this is a little tricky, but you do have to convert between U bar and H bar back to U's and H's, or solve the whole problem in not per unit mass, but in per unit amount. Sometimes we do that. We do it. Okay. Here's a problem, and then I have this question. Carbon dioxide, and I'm going to say right away, carbon dioxide is a great ideal gas. All right? So let me just say this is an ideal gas. Is initially at 6 bar and 400 Kelvin in a piston cylinder assembly. It undergoes a process to a final temperature of 298 Kelvin, while the pressure-volume relationship is equal to PV to the 1.2 is equal to a constant. So pressure times volume to the 1.2 is equal to a constant. That's what this is. It's a polytropic process. That's what it is. Before we answer these questions, answer this clicker question. If an ideal gas undergoes a polytropic process such as PV to the 1.2 is equal to a constant, is it also true that PV is equal to MRT or PV is equal to RT or whatever form of the ideal gas equation is also true during the same polytropic process? Or does this result sort of trump the other result or the other equation? All right, let's see where we stand. Most of us say that it is true, that yes, that both of those are true. All right. So a lot of times you have a polytropic process, and then sometimes it's a carbon dioxide or other ideal gases undergoing a polytropic process. You can have steam, which is not an ideal gas, undergoing a polytropic process. But sometimes you have a polytropic process described by that equation, and it's an ideal gas. And somehow, every now and then students will say, well, that must trump the other one. If this is true, then this can't be true. No, they can both be true. They can both be true. It can always be an ideal gas, and it can also undergo a polytropic process. So the answer is A. Well, now let's solve this problem. Yes, sir. Yeah, that's right, exactly right. So let's go ahead and solve this problem. Carbon dioxide is initially 6 bar, 400 Kelvin in a piston cylinder assembly. It undergoes a process to a final temperature while the pressure-volume relationship is given. Determine the final pressure, then the work, and then the heat. All right, so sometimes a lot of times I'll put a little illustration, there's our piston cylinder. We're interested in this trapped amount of gas undergoing some sort of expansion or compression process. Okay. Make a list of the properties. Let's put P for pressure. Let's put T for temperature. And you can put cap V or specific volume, whatever the preference is. Now, is the mass changing from the initial state to the final state, or is the mass constant during the process? It's a closed system, constant mass. Okay. So let's put in our value for P1, 6 bar, temperature 400 Kelvin. We don't know the initial volume nor the initial specific volume. Let's take a look at P2. What's our final pressure? Well, that's what we want to find. Isn't that the answer we need to get for part A? And then T2, oh, that's 298 Kelvin. And then we don't know V2 and we don't know V2, either one of those. All right. Let me ask another clicker question. Is this true? Is the specific volume initial equal to the specific volume final? Yes, answer A. B, no. All right, what do you think? There's nothing in the problem statement that says it's the same specific volume. If you had the same specific volume, would that piston have moved? The piston would not have moved, right? Because what's the specific volume? Volume per unit mass. Mass didn't change. So, all right. Now, so how are we going to solve this problem? Well, we have to say that during the process, both P1, V1 to the 1.2 and P2, V2 to the 1.2, they're equal. So this is equal to P1, V1 to the 1.2. Isn't that true? It's equal to a constant. Likewise, this is that it's a polytropic process. You could say it always behaves as an ideal gas. What does it mean to always behave as an ideal gas? The ideal gas equation plus U is a function of T and H is a function of T. But for right now, the ideal gas equation, we could write it like this. We could say P1 V1 divided by T1 is equal to NR bar. Is that okay for the ideal gas equation? Look good? Come over here. P2 V2 divided by T2. Is that also equal to N R bar? Is that also equal to N R bar? Is N bar, is this the same as this? Hence, I can rewrite this to say that's equal to P1 V1 divided by T1. Where did that come from? Is the ideal gas equation. The trapped amount of gas, it's undergoing a change in pressure, temperature, volume, but the ratio P times PV divided by T is a constant. So what you'd have to do to solve this problem is you're looking for P2. You've got a P2 here, and what you want to do is you want to get rid of the V1 and the V2 in this equation by substituting. So I'll take the ideal gas equation and put something like, well, maybe, how about this? P2 is equal to P1 times V1 over V2 to the 1.2. Did I do the algebra correct? Guess what? This is a great algebraic exercise. This problem is going to work your algebraic side of your brain or muscles. All right? So now, how about I take this ideal gas equation and I say V1 divided by V2 is equal to, V1 divided by V2 is P2 over P1. That looks good. And then I'll have T1 divided by T2. Did I do that one correctly? Yes? Substitute in, so we'll get, maybe I'll do it this way. I'm going to do it this way. Just try to make it clean. P1 over P2. All right. 1 is equal to P1 over P2 times, when we substitute, we get P2 over P1 to the 1.2 times T1 over T2 to the 1.2. Did I skip too many steps so you follow? Give me a thumbs up if you follow. How many people need more time to process? Did I make an error? How many people agree with me, no error? Thumbs up. How many people, I think you got an error, Professor. All right, well, if I have an error, let's proceed. Okay, so what is, it's 1 equal to, if I multiply right here, I'll have, what will I have? I'll cancel the, that's a P1, I'll cancel that. It'll be P2 over P1 to the 0.2 times T1 over T2 to the 1.2. Is that good? Is that equal to 1 is equal to P2 over P1 times T1 over T2 to the 1.2 divided by 2, that exponent? This is 0.2, right? Is that okay? Professor, I passed that math class already. I don't want to see that math anymore. I don't want to see it. Is it, did I write it not clean enough? This is the 1.2 divided by 0.2. So P2 is equal to P1 times, oh boy, you could put T2 over T1 to the 1.2 divided by 0.2. You could do it that way. Okay, if we substitute numbers, and if somebody has a calculator, please, I'd appreciate it. So P2 is equal to 6 bar times T2, 298 Kelvin, divided by T1, 400 Kelvin, all raised to the power 1.2 divided by 0.2. And so when you get it, raise your hand, I'll call on you, and then I want you to read the number to me slowly on your calculator. We got one person working. You got it? Thank you very much. Thank you for the confirmations. So, put it to 4 digits. 4 significant digits. Answer to part A is done. Whew. That was a lot of work. All right. Let's go to part B. What is the work transfer? Now notice, what are the units that they're asking you to calculate it in? Are you going to use cap W or lowercase w for this answer for part B? Lowercase w. Is that equal to the integral PdV? Yes, it is. And in this P, you would put this constant divided by V to the 1.2 dV. Okay. If P cap V to the 1.2 is a constant, then P lowercase v to the 1.2 is also equal to a constant. I didn't say the constants are the same, they're just a different constant. We don't know the amount of mass, but if you just take both sides of the equation, or the equation divide by m to the 1.2, you get specific volume, right? So now, I'm not going to do the rest of this work. Where is it outlined in the book? Very clearly, very cleanly. The very last example problem in chapter 3. They do that work, polytropic process. If I had a little more time, I would do it. I can do it if you want me to do it, maybe right before the exam, Monday. Go step by step on the tedious algebra, the calculus, I should say, on doing that integral. But that integral comes down to P1, V1, put it on a per unit mass basis, V1 minus P2, V2 divided by 0.2 for this problem, which is K minus 1 or N minus 1. And then we look and we say, hey, it always behaves as an ideal gas. Can I replace that PV by RT1 and RT2? You sure can. And then you get that the specific work is 96.3 kilojoules per kilogram. Yes, I want you to work through the algebra and the calculus on that. Next part, part C. What is the heat transfer? How do you think we get that lowercase q? Q is equal to W plus U2 minus U1. Where'd that equation come from? First law for the process. Exactly correct. Now, what about this carbon dioxide? If I really want to do a great job on those U's, go to the table, carbon dioxide, get U bar at 298, that's T2. So this is U bar 2. And then at 400, that's T1. And this is U bar 1, true? But then I have the molar mass to get it to on a per unit mass basis. So when you calculate Q, I'm out of space, 24.5 kilojoules per kilogram. Let me ask this. Is the gas expanding or being compressed during this process? Is the gas expanding or being compressed during the process? Good clicker question. Let's go with clicker question A, it's expanding, or B, the gas is being compressed. Answer A, the gas is expanding. Answer B, the gas is being compressed. All right, sorry, we're out of time. Oh, you didn't get it in? Got to watch the time, sorry. All right. It is expanding. How did you determine that? Is the work positive or negative? Positive. All right, not a clicker question. Is it being heated or cooled during the process? Is it being heated or cooled during the process? All right, it will be a clicker question. Is it being heated, answer A, or cooled, answer B, during the process? All right. Did we abandon the thermodynamic sign convention, or did we stay true to the thermodynamic sign convention where a positive Qin is being heated, a negative Qin is being cooled? Answer to part C is a positive, 24. Is it being heated? It's being heated. Oh. I need to thank you very much for your attention.